So today we're going to talk about how to find limits analytically, or using different algebra techniques to find the answer to limit problems when plugging in your c-value just doesn't work. So the first type is going to be called the cancellation technique. And for this one, we're going to do an example. So for the limit as x approaches 3 for x squared minus 9 over x minus 3. So if you plug in the 3 here for your c value, you get 0 over 0, so that's not an answer you can work with. So what you're going to do is the first step is going to be to factor the top and the bottom, because cancellation technique, the word cancellation, you want to try and cancel something eventually. So if we factor this, we're going to get the limit as x approaches 3, factoring that difference of perfect squares in the top. We get x plus 3 times x minus 3. And since x minus 3 in the bottom is already a binomial and we can't simplify it any further, it's just going to leave it as is. So now we can see that we actually have a common factor, that x minus 3 that's the same in the top and bottom. So we're actually going to cross that out. We're going to simplify a little further. So now we're going to rewrite what we have left. So we have the limit as x approaches 3 of just x plus 3, since we just have a 1 in the bottom. So now we have it to a point where plugging in our c value will give us an answer. So plugging in that 3 gives 3 plus 3, or 6, as our final answer. So the cancellation technique, if you can factor the top or bottom, you want to try factoring first, canceling out any common factors, and then plugging in c after you simplify. And that's the main gist of it. The second technique we're going to go over is for functions that have radicals in them. So the rationalization technique is we're going to rationalize what we have with radicals. So for this example, we're going to do the limit as x approaches 0 of the square root of x plus 1 minus 1 over x. So again, plugging in for 0 would just give 0 over 0, which is an indeterminate form, which means that we have to do more before we can say what the answer is. And when you have a square root and you get that sort of answer, what you want to do is multiply in by the conjugate. So the conjugate here is going to be the square root of x plus 1, because the conjugate is just the same thing with the opposite sign in the middle. Now, a piece of advice for you is you don't want to distribute through the bottom. You want to leave it separated in the bottom and only multiply and distribute in the top. So only multiply the conjugates together. And you'll see why at the end of this. So we want to remember to FOIL properly. So if we FOIL through, the square root of x plus 1 times the square root of x plus 1 gives x plus 1. And then we have positive 1 plus the square root of x plus 1. Then negative 1 times the square root of x plus 1. And then negative 1 times positive 1 gives minus 1 on the end. And then, like I said, we're not going to distribute through in the bottom, so we're just going to rewrite it. Now you can kind of see that those two middle terms at the top, the square roots, they cancel because they're the same thing with opposite signs. So now all we have left is the limit as x approaches 0. And if we simplify too, since we have x plus 1 and minus 1, we really just have an x left in the top, over this x times square root of x plus 1 plus 1. So now that we've simplified, done our rationalization, all of that, we can see that we have a common factor left in the top and bottom. We have that x, so we're going to cross those out, just like we did in the last problem, and rewrite what we have. So we have the limit now as x approaches 0, and we crossed out the x in the top, but that doesn't mean we have nothing in the top. It means we have a 1, because we need a placeholder, and then we just have that square root of x plus 1 left in the bottom. So now if you plug in for 0, or plug in your c value, you see that you get an answer. So we get 1 over the square root of 0 plus 1, or 1 plus 1. And the square root of 1 is 1, so our final answer is going to be 1/2. So that's the gist of all of these sorts of problems. So when you have a square root in the top or bottom of your fraction and it's preventing you from getting an answer just from plugging in, you want to do this rationalization and multiply in by the conjugate over itself and then simplify. So So then we have limits with complex fractions, and complex fractions are just fractions within fractions, and we don't really like those in math, so our first step is always going to be to get rid of them. So if we look at the limit as x approaches 0 again of 1 over x plus 4 minus 1/4, and all of that over x, we can see that we have fractions within fractions, so complex fractions. The first step is going to be to just get rid of them. We don't want complex fractions, we just want a regular old fraction with just terms in the top, terms in the bottom, no fractions there. So in order to do that, you want to multiply in by something to cancel with the little denominators. And in that case, it's going to be something to cancel with the x plus 4 and 4 in the top, because those are our like little functions, little fractions. So we want to cancel with those. So to do that, we're going to multiply in by 4 times x plus 4. And usually you're just going to multiply in by the product of the two denominators that you want to cancel with, or however many denominators you want to cancel with. It could be more than 2. So now we're going to distribute through and then simplify. So when we distribute through, we get 4 over x, 4 times x plus 4 over x plus 4 minus 4 times x plus 4 over 4. All of that over x times 4 times x plus 4. And again, we aren't going to simplify and multiply through in the bottom because it's going to make our common factor harder to see. So now we have common factors in the top fractions that we can cancel with. So we can cancel with this x plus 4s because there's one on the top and one on the bottom. And same thing with the 4s in the second fraction. So now we've actually gotten rid of our complex fractions, which is exactly what we wanted to do. So if we simplify, we get limit as x approaches 0 of 4 minus x plus 4, and those parentheses are really important and you want to make sure you don't forget them because we have to distribute that negative sign over 4x times x plus 4. Just going to move that 4 outside of the parentheses. And so now we're going to distribute our negative sign and then simplify. So if we distribute the negative sign in the top, we're left with the limit as x approaches 0 of 4 minus x minus 4. So those two 4's cancel out with each other and we're left with a minus x. And then we still have our 4x times x plus 4 on the bottom. So again, we see that we have a common factor. So we're going to cancel our common x's and then rewrite what we have and see if we can plug in. So because of that negative sign on the x that we had in the top before, we have to remember to put a negative 1 in the top now because that's what's left over. And then we have 4 times x plus 4. So now plugging in for 0 will give us a number which can be our answer. So we're going to get negative 1 over 4 times 4, or negative 1 over 16. And that's going to be our limit here. So when you have limits that deal with complex fractions, just get rid of them. And then move on, simplify, and cancel out any common factors and plug in your c-value to get the answer. So now we're going to switch gears and switch from talking about methods you can use to manipulate functions to a theorem that lets you kind of see something else. So this is called the Squeeze Theorem, and you'll see why when we draw a picture of it in a minute. So this says that if you have three functions where h of x is less than or equal to f of x, which is less than or equal to another function g of x, for all x values in some open interval, so over some interval in the x-axis that has the c value that you're going to take the limit at, and it's somewhere. And this ordering of them, the h of x less than or equal to f of x, less than or equal to g of x, might not be true at c itself, but it's true everywhere else in the interval. And if we have then that the limit as x approaches c of h is equal to L, and the limit as x approaches c of g is equal to L, then we can conclude that f of x exists and the limit is equal to L. And that's because f of x is sandwiched in between h and g. And so we're going to draw a picture now to try and illustrate that for you. So if we draw a picture, we're just going to draw a quick graph here. And then we'll label them. So this is going to be h of x because it's the lowest, f of x because it's in the middle, and then g of x because it's at the top. So we can see that it meets all of those qualifications for the ordering over some open interval. And so we're going to label this point down here as C. So you can kind of see that the limit of h and g has to be over here at L. And so if you didn't know how to take the limit of the function f of x, if you knew what it was equal to, if you could get a picture like this where you had two other functions squeezing in from both the top and the bottom at C with the same limit, then it must mean that the function in between, or your f of x, has to have the same limit as well. So this is an important visual piece of information to keep in mind. So now we're going to talk about limits with trig. And I know not a lot of people like trig, and it's really confusing for a lot of people. So we're going to talk about these two special trig limits that you really need to know and probably have memorized to help you on tests and quizzes and stuff like that. And the first one says that the limit as x approaches 0 of sine of x over x is equal to 1, which if you watch the video on how to find a limit numerically, that was the example that we did. So you did see that it was equal to 1. And the second special trig limit is, again, the limit as x approaches 0, but this time it's 1 minus the cosine of x over x. And this is going to be equal to 0, which you could, again, show to yourself using a numerical or graphical approach. So these are really useful when you're solving example problems. The example problem we're going to look at is the limit as x approaches 0 of the sine of 3x over x. So now before you just try and jump to an answer, let's take a look back at the definitions for these special trig limits and notice that the x inside of the sine matches the x in the bottom. So when those two match, then you can use that the limit is equal to 1. But down here we have 3x inside and x on the bottom. They don't match, so we're going to try and change that. So we want a 3x in the bottom, so one way we can do that is multiplying the bottom by 3. But if we multiply the bottom by 3, we have to multiply the top by 3 as well, so we don't change the value of anything. So now we get, forgot to write my limit sign. So we get the limit as x approaches 0 of 3 sine of 3x over 3x. And now we have that these two things on the inside match, and that 3 in front of the sign right here, that's just a scalar multiple or a constant, so we're going to use that limit property that says we can pull it out front. So we're going to rewrite this as the limit of 3 times the limit as x approaches 0 of sine of 3x over 3x. And now that those 3x's match, we can replace the limit with that special trig limit and say that this is just equal to 3 times 1, or 3. So that's one way you could approach trig limits if you can try and manipulate them into looking like one of those special trig limits that are above. So since trig is so complicated for some people and really just is hard for a lot of people to understand, we're going to talk about 3 different methods and tricks or steps to try when you're doing limits that have trig in them. And the first step is going to be those special trig limits. So you're going to try and manipulate, just like we did in that last example, to make the problem look like one of those special trig limits, so you can just use those rules and find your answer. The second step we're going to do is what I'm going to call the rewrite and rearrange step. And this just means you're going to rewrite things and then rearrange them and simplify to try and get an answer. An example here would be to rewrite tangent of x as the sine of x over the cosine of x, and then to simplify and try and rewrite things from there. And the third and final trick I'm going to suggest is using trig identities. And trig identities, your calculus book might have a list of them for you, or you can easily Google them, and a bunch of different websites and resources will pop up to give you a list of them. And you can use different trig identities to substitute in and simplify and try to rewrite and manipulate your function until you have something that you know how to work with. So those are 3 steps that you could try and take when you're trying to find the limit of something that involves trig. So thank you so much for watching. I hope you have a great rest of your day, and see you later.